Okay, so one more reduction. All right. So let's look at a new problem that is the vertex cover problem. So in the vertex cover problem, we were given a graph and a set of vertices. S is a vertex cover if every edge has at least one endpoint in S. Okay. Simple as that. That is why it's a vertex cover. Basically, if we have the following graph, then these edges here would be the vertex cover because every edge in this graph ends in one of these three endpoints. Okay, this isn't the only vertex cover. There are larger vertex covers, but with vertex covers, we want to see how small we could get it, right? I mean, the trivial example is that the set that includes all the vertices is a vertex cover, right? But we don't want that. We want to define something more interesting. We want to define, is there a vertex cover of less than or equal to k in the graph, right? It would be cool if, for instance, what if the vertex cover is, if there is a vertex cover of, I don't know, n over 2, right? That would be interesting. What if there's a vertex cover of 1 in the graph? That could tell us something very interesting. What would a graph with a vertex cover of 1 look like? I'll give you a moment to think about it. Okay, a graph with a vertex cover of 1 would effectively be star-shaped. It would mean that there's one vertex for which every other edge ends at. Okay, so vertex cover gives us a very interesting idea of the structure of the graph. It could be used in a variety of applications, right? It's not just like a mental exercise. So the question is, can we prove, is this an easy problem? And I'm going to tell you no. Let's say your boss gave you this problem, you spent a couple days toiling away at it, and you didn't make any progress, right? You're able to calculate it brute force-wise. If you take every subset of vertices in the graph and then calculate if they're the vertex cover, then you could probably find a solution to it. The only issue is that that's a hell of a long time. All possible subsets. It's a power set, so 2 to the n possible subsets. Not doable, not feasible for larger graphs, or even not trivial graphs. The question is, can we relate the independent? So we get a sneaking suspicion that vertex cover is hard. So we want to prove that it's hard. So in order to prove that it's hard, we need to take another known hard problem and relate it to that. We know independent set is hard. So the question becomes, can we relate independent set to the vertex cover problem? Okay. So here's the issue. And actually, before we go through the proof, I skipped over the visual hints. But let me go back to the visual hints. Right. No. Okay. The visual hint for this is that I told you that this graph, this was a vertex cover for this graph. Do you remember what the independent set for this graph was? So this gives us a pretty strong hint about how vertex cover and independent set are related, right? Namely, if you have an independent set with k vertices, then all the vertices that are not in the independent set would probably form a vertex cover, right? That's important. I feel like that's important. Okay, so here's how we formally prove it. If we have a graph and S is an independent set, and then not minus s, we argue that if S is an independent set in that graph, then the rest of the vertices are a vertex cover. So how do we prove that? Well, let S be the independent set for any edge that is coming out of that set. One of them is not part of the independent set. All right? We know there are no edges that go between the nodes of the independent set, right? So there are no edges that go between the nodes of the independent set. So every edge, either one is not part of the independent set, or the other. One endpoint is not part of the independent. One of the endpoints is not part of the independent set. Okay, so either of these endpoints. So either one of the endpoints is part of the independent set, or both of the endpoints are, either one of the endpoints is part of an independent set and one is not, one of the endpoints is part of vertex cover, or both of the endpoints are part of the vertex cover. Okay? So if every edge ends in a vertex cover, it means that that vertex cover covers the entire graph. That's the definition of vertex cover. So therefore, if you have an independent set of size k, then you have a vertex cover of size n minus k. Okay? So if we have a graph with n vertices in an integer k, assuming we want the problem to find if there is a independent set of k vertices, then all we need to do is simply relate it to if that graph has a vertex cover of size n minus k. Okay, that's how the two problems are related. If one has that's how the two problems are related. So if g of k is an instance of independent set, then g of n minus k is an instance of vertex cover with the same answer. And so therefore we could get the following reduction: independent set is reducible to vertex cover, or vertex cover is reducible to independent set. And we could show the reduction like so. And all the reduction itself does is transform this second number from k to n minus k and y. Okay. One thing I want to specify before we end this lecture is simply that this polynomial time, we'll go more about it, but this reduction in p means something. And this is what's known as a Karp reduction. And we're going to go over Karp reductions more next time, but what this is doing is showing that independent set and vertex cover are related to each other in polynomial time. And there are other instances, other problem relations, that we could relate one problem to another in exponential time or in super polynomial time, right? So the reason we show this is because this is an efficient reduction. Polynomial, when we talk about efficient algorithms, we're always talking about something that's polynomial time in nature. So whenever we say efficient in computer science, we will always mean polynomial. So if we have an efficient reduction, we should say that it is polynomial time. Therefore, if this is a polynomial time algorithm, then this has to be a polynomial time algorithm because the reduction is also polynomial time. Does that make sense? I mean, hopefully that makes sense. And we're going to talk more about it in the next lecture. Okay, but for right now, that's all we have. All right, see you in the next one.